For this final lesson of vectors, we are going to find the distance from a point to a line in 2 space, a line in 3 space, and we'll also find the distance from a point to a plane. Okay, so we're going to be doing three different things here, okay? Similar setups for each of them. But let's take a look, first of all, the distance from a point to a line in 2 space. Okay, so we are looking specifically, we've got our ordered pair. All right, we know that the shortest distance between any two objects is a perpendicular distance. Okay, so that's what we're going to be seeing. So what I want you to take a look at is the diagram that we have. All right, point P is our point that's off the line somewhere. Our line is could be considered this through A and N. All right. N is the capital N. All right. Is the point directly under, we'll call it P, so that PN is perpendicular to AN. All right. The normal vector of the line, all right, is perpendicular already. Right? And since it's a vector, we know we move it anywhere. So what we're saying is that we can move the normal vector so it goes through the point P, all right? And then we can have that N and P are on N and the normal vector, all right? AP would be the vector that's formed from a point A on the line that we know, all right? We know this point, just like we've developed this in the past, okay? So from this setup, we can see that that the distance that we're looking for, right here, is basically the magnitude of the projection of AP onto the normal vector, all right? Now, it may be a little harder to see it that way when we look at it like this, but if we move AP so that its tail is at capital N, right? And it goes up here, then you can see that this is the vector AP as well, and its projection onto the normal vector, right? This perpendicular part here, you set up this parallelogram, right? So that NP, the magnitude of NP is the distance that we're looking for from the point P onto the line. Okay, so hopefully you can and see that. So it is basically we're looking for the scalar projection. We're going to take a look and see how we develop it. So we start off with the magnitudes of the vector projection itself. That's what we're looking for here. All right, between A, P, and N. All right, the normal. Substitute the values in. Okay. And now in this next line, all we're doing is we're doing some reductions here. The magnitudes are positive magnitudes. You've got the magnitude at the bottom squared times the magnitude, all right, at the top, one of the numerators. So we just reduce down, and so we end up with just a single magnitude at the bottom, all right. With the dot product, all right, if you take a look at how the dot product is formed, we're using, I guess the regular way we're doing it, we're using the point P, the XY, the point A, the A1, A2, all right, the normal vector, AB. When you dot that and rearrange, okay, you've got the expression on top, and we know that the combination of these two is the C value. I added that in at the bottom here, okay, and this is our equation for the distance into space, okay, from the point P. So when we have this down here, remember that P is our XY, all right? The normal vector is the AB, all right? So I just put a note here to say that, we can play with the magnitudes properly like we did above, okay? So that's not a earth-shattering note, okay? Let's use this as an example, okay? So we can understand what we're doing here. We've got this line in 2 space. We can see that it's the scalar equation of a line in 2 space, right? We end up with we've got a point that's not on the line, right? It doesn't satisfy the line. It's not 0 on the top. How do we find the distance from that point? Okay, we've got our formula, all right, and I would make sure that you have it with you, all right, so you can always go to it when I ask you that on an assessment, hint, hint, all right. Substitute the values in. Look at the normal vector, right, the line itself, the -4, the 6, the -7 from the line stay. You substitute the -3 and the 5 into the equation up top. It's the absolute value. You end up with 35. You find the magnitude of the normal vector. We notice that the normal vector here is -4, 6. You find the magnitude at the bottom, all right, and you've got this 35 over root 52. If you want to rationalize the denominator, you end up with the final one here. Okay, make sure you understand how to work that. So that is the distance in 2 space, all right? Now, in 3 space, we don't have this scalar equation. Remember, in 3 space, the scalar equation is of a plane, not of a line. So we have to come up with another method for the distance between a point to a line in 3 space, all right? So let's take a look at the diagram that we have, all right? I've put a little bit on here as well, but you can see that we're going to be using this line that we have, let's call it L1, all right, has a direction vector, right? Remember that L1, when we do this with the vector equation, all right, has our point, and we use this as the position vector, so A1, A2, A3, and we add on our direction vector, right? We can say M1, M2, M3, okay? So if we see how these are formed, we've got our angle theta, all right, between the direction vector M and the vector formed by the point A that we know on the line and the point P somewhere off the line, okay? We know that the distance is a perpendicular distance. We know that for a fact, okay? So when we complete this triangle, we can use, because it's a right angle triangle, we can use the opposite of theta and the hypotenuse. Opposite, distance, hypotenuse, magnitude of AP. So that is sine theta, all right? So the first thing that we see is that the distance is the magnitude of AP times theta itself, okay? Now, since we have theta here, one of the other things that we also know is that the cross product deals with sine theta rather, okay? Since we have sine theta, we use cross product. Well, the cross product, because theta is between the direction vector M and the vector AP, we can use the magnitude of the cross product, by definition, is the magnitude of the direction vector times the magnitude of AP times the sine of theta. So if we were to just simply divide both sides by the magnitude of M, okay, the direction vector, the magnitude of the direction vector, we get this expression. Notice that the magnitude of AP times theta is the distance that we're looking for. So the distance from a point in 3 space to a line is this equation right here. We use the magnitude of the cross product divided by the magnitude of the direction vector. Okay, let's take a look at this example. So we have our point that's listed as P, negative 1, 1, 6. We have our line, which gives us our direction vector, right? And we have our position vector OA that we know, okay? So we know another point that's on the line, 1, 2, negative 1, all right? We have then our vector AP. We find the cross product between the magnitude and AP, all right? And then we calculate the magnitudes, all right? Take a look at those. Right? Make sure that you have this as well, okay? I would highly suggest stop the video, go through the algebra yourself, make sure you come up with the same thing, okay? And then you can press play again and move on to our last step. The last thing is the distance from a point to a plane. Now, we deal with the planes in the scalar equation a lot, all right? So this is very, very similar to the point to a line in 2-space because it uses a scalar equation as well, all right? The setup is almost the same. And the reason why it's almost the same is if we take a look at this diagram, you know, I quickly drew. P, you can see, is outside of the plane. The plane is listed as the green, all right? The distance is the perpendicular distance straight down, okay? Perpendicular distance. Why is that important? Well, we know that the normal vector to a plane is perpendicular by definition, right? So if we have the normal vector, right? The A, B, C components or the coefficients in front of X, Y, and Z. We have those automatically, right? We could set up like we did before with that line. We called this point here, that intersection point, N, right? It's the same setup, exactly the same setup, all right? In this case, we're using the plane itself. So because it's the same setup, we're still using the projection, right? So we want the magnitude of the projection of AP on to the normal, all right? And again, you can go back to the line and see how that works out. It's the same thing here, right? Yeah, I move AP, you know, let's make it red, move AP, right? So that AP is now over here. Again, it's the projection onto the normal. The normal vector moves along here, right? So it comes straight onto it, perpendicular there, and then we can go with the projection, okay? So go through, same thing here. Again, this is the magnitude squared. I didn't put that down. Let me, right, missing that part on this, okay? And you can work your way through. Again, we have a reduction from the magnitudes here with the one there. We end up with the denominator, okay, is the magnitude of the normal vector. The top portion, again, very similar. What you do is you have the magnitude of the plane. However, your XYZ or XYZ is actually the point XYZ that you substitute in. Okay? So, you know, you have everything there. The interesting thing, or the extension, so that you're not just saying, okay, what's the distance between a point and a plane, is how do we find the distance between two skew lines? two skew lines. That's the extension to this, okay? If I'm already telling you L1 and L2 in this case are skew, how do we find the distance between them? Well, two parallel planes are the same distance apart everywhere, right? We've had that before. If you look at the side of a plane, right? Pi 1, pi 2. No matter where you take the distance, it's all the same, right? We just don't know where the distance is if we're dealing with two skew lines. So here's what you do. We know how to create two parallel planes from two skew lines, okay? So what we do is we form a parallel plane. Take the direction vectors of the two skew lines, cross them to find the normal vector to both of these planes that we're going to have, right? It's normal to both lines. You can then take the point on line 1, which would be the point -2, 1, 0. Substitute that into your equation for the plane, right? You already have, if you do the cross product, you have the AX plus BY plus C, Z, and you solve for D, right? By putting in A1. How do you find the distance now? You've got a point on L2. If it's on L2, it's got to be on the second plane, right? So you use our formula that we just discovered to find the distance between the two. Okay, that's the idea. All right, so you can try that out. Go through the assigned work on here, which is all distance. Okay, 2 space and 3 space. All right, and then this is the end of your vector work. All right, good luck.